So yeah, so I guess Alper just mentioned. I think he and his family were in Los Alamos for several years, and we became very close. We stayed in touch, and I really appreciate him gave me this opportunity. So he also asked me to say a few words about Los Alamos National Lab. So I'm assuming some of you have heard about this place. There's, if you think back of the past 60, 80 years human history, Los Alamos probably will come up because this is literally one of the places where it changed the human history during the Second World War. What I found is this picture. So Los Alamos is in northern New Mexico. It's a very mountainous area. As you can see, this is where we call Jemez Mountains, where we can ski in there. And then at about halfway, you have this very fascinating landscape, which is we call mesas. So all the green area you see are the valleys where you grow trees, and the snow and water will run through there. And then in between the valleys are those the mesa tops. You can see, and there's one mesa, another mesa, another mesa, another mesa, and another mesa. So people can live on different mesas, and in direct distance are fairly close, but you really have to go all the way to the mountain and then go over there and to visit them. So it's pretty interesting way of living. And the lab is way over there, and the people live over here, and that's what we call downtown area, where you can actually get groceries. We only have one grocery store. That's very different from a metropolitan city like Singapore. Sorry, it's also a country. And there's so this was funded back in 1943. It's called Manhattan Project. And for several years, it's probably had the highest concentration of world-renowned scientists and engineers for several years, and all devoted to the sacred project of developing atomic bombs, which eventually changed the course of the Second World War. And after the war, U.S. government felt it's necessary to continue this type of research, maintain this capability, and eventually, even though many world-renowned physicists or scientists left the lab after the war, they kept this place and turned it into a scientific laboratory up until today, under Department of Energy of U.S. government. The lab does a wide range of basic research as well as applied research. Myself, as an example, I work mostly in astrophysics. I will not explain why they want astrophysics, even though it's a Department of Energy lab, as you probably will figure out later. On the right, I'm showing this person should be famous to all physics students. Is Robert Oppenheimer, and he was the founding director of the laboratory. On a more personal note, lower right here is another famous scientist called Sterling Colgate. Many of you might have used toothpaste Colgate brand, right? So I don't know the Chinese translation of that. Albert, you know? Oops.
Oh, we know the toothpaste as Colgate. We also don't know what the Chinese translation is.
Oh, sorry.
Yeah.
Okay, somebody is saying something. So he's a member of that family. He's my mentor for almost 20 years, and he passed away in 2013. when Sterling first met, so Sterling told me many stories about this place, because when he was 16, 17 year old, he was attending a ranch school in Los Alamos. His hometown is back in New York, where the big metropolitan area, the company, all the riches are. But his father thought he needs to be disciplined more and sent him to northern New Mexico, this little ranch school, which apparently it's boys school, but it's extremely high level. So many very famous people came out of that ranch school. So he was still in high school when Oppenheimer and General Groove showed up and basically told them, you all need to graduate in a few weeks because the government is taking over this town. And back then it wasn't even a town, it was just a little school there. And he apparently, so Sterling quickly graduated, got his high school diploma and went to Cornell. He later on became a famous physicist himself, Sterling, and was known for supernova research and other things. And so you may have noticed this little airstrip. That's a little airport. So only small airplanes, very small airplanes, twin engine, maybe single engine airplanes, jets cannot land here, helicopters. So I took off several times in his personal airplane on a little runway, and we will fly to southern New Mexico. There's another university called New Mexico Tech, where we have liquid sodium experiments going on, being carried out there. Sterling served as the president of New Mexico Tech for about 10 years, and before he did more research at the lab. Anyhow, so it's a great place if you have a chance to visit, and also maybe spend the summer here doing an intern. I think we do have summer programs for students. I'm unclear on whether international students can come, but do keep this in mind as you look for student fellowships and postdocs. Okay. Albert, do you want me to say more about the lab, or we should move on to astrophysics?
Yeah, you can move on. Thank you very much. It's great.
Yeah. Okay, so I want to take this opportunity to share with you on a subject that's been very fascinating and very interesting, and has a lot of implications even for general public. So it's a topic of from dust grains to planets. I've been fortunate to have a large number of colleagues, students, and postdocs working with me over the years on this topic. So I won't go through all the names here. Oops, I apologize that it's not listening to me. The idea here is that we have a fair number of scientists and young people working with us on theory and simulation. And then we collaborate around the world with other observers. And so we use their data and observations to test our theory and vice versa. And it's been great fun. And we've been able to convince different funding agencies to support us for this basic research effort. So I'm assuming most of you don't work in astrophysics, so I just want to lay some, give you some very basic information first before I dive into some of the details. So okay, this should be familiar, hopefully, to all of us, right? So our sun, and either whether you call 8 planets or 9 planets, depending on what your preference are. So there's Mercury, Venus, and this is our home Earth. On Mars, recently, we just, US just had Perseverance rover landed on there, was extremely exciting. Then this asteroid belt, and Jupiter, Saturn, Uranus, Neptune, and Pluto. So this is our home, and later on, I will point out that all those four are called gas giants. They're a lot bigger and more massive than the four inner ones we call terrestrial planets. They're rocky. In other words, they're rocks. They're dust, rocks, boulders, and those ones, most of the mass are in gas. So, for example, Jupiter is 300 times more massive than Earth. Okay, but Jupiter, if you really send a graduate student to dive into the atmosphere, you'll find that 90% of the Jupiter planet is gas. It probably has a small core that's maybe 10 times the size of Earth, but most of it is gas. So if you look at distance scale, you line them up on this logarithmic scale here. Just the distance between Earth and Sun, we call it 1 AU, astronomical unit, AU. And if you use that as a ruler, Saturn is at 10, Jupiter is at 5. And the boundary of what we call solar system is when we define it as the sun makes a wind of plasmas, particles, magnetic fields. They finally interact with the interstellar medium. So inside of this heliopause, it's all solar material. The plasma, the particles and material here inside this cocoon all came from the sun mostly, and then beyond which is interstellar medium that's dominated by other processes, not by the material from the sun. So the nearest star is 10 to the a million AU, almost a million AUs away. So you can see we are pretty self-isolated in a way that it's really minuscule in the distance scale and length scale, but otherwise we're fortunate that our Earth's atmosphere isn't as dense as Jupiter, so that humanity can actually look out into cosmos and actually detect anything. If the atmosphere, like on Venus and others, is too thick, we probably can't get much light through, and we won't be able to do astronomy. So I probably won't have a job. And another very fortunate thing is that the whole solar system is located pretty far away from our galactic center. In fact, it's almost on the not quite on the edges of the Milky Way galaxy. That again may be very fortunate. If we get too close to the center of the galaxy, the environment will be very violent. The high energy radiation, the high energy particles, the intensity will go a lot higher, and the life there might not be as cozy as on Earth. Anyhow, so this is the system that was studied back in 80 whatever, right? So the Chinese even saw supernovae, and in the 1600s, 1700s, 1800s, people actually figure out the motion, and Kepler figured out the motion, the Kepler law of planets, and so on. There's a big debate as whether Earth or Sun is the center, and finally understood that the Earth is not the center, Sun is the center in this whole system. This is a movie I found online. So in this talk, let me go back. In this talk, what I really what I mostly want to say is that it turns out when we observe other stars like the sun, then one question we ask is, do they have planets like solar system? So that's one natural question. The second question would be, if they do have planets, do they arrange the way like solar system? Do they also have gas giants or terrestrial planets like this? Of course, those questions eventually lead to the very, very important, interesting question is, are there planets like Earth can sustain life as we know? And so along with those observations and set of questions, we will be looking at how those planets were formed using observation, theory, and simulation. And at the current stage, we have far more questions than answers, and that's where I will probably end. And my ultimate goal is, of course, to get you all excited about subjects like this, that thinking about perhaps pursuing a graduate career in astronomy and astrophysics, if not in Singapore, maybe somewhere else. Okay, so, and also feel free to interrupt and to get clarification, especially if the subject is relatively new to you all. So what I just showed here is a system where you have a single star with lots of planets, right? And the size scale here is maybe 100 AU at the most. Now, if you zoom out and say, wow, how about other stars and how do other stars actually form? What's their environment? And this is what I was going to show. I found this movie. What I'm showing here is dusty gaseous cloud, and the size of this is about 1 million times a solar system, so it's huge. And you're going to find that inside which stars will form, and around that star, planets will form. This is kind of partly observation images, partly simulation, and partly imagination, all combined together in making this movie. So and remember, this is about 10 to the 6, or now 10 to the 5 solar system size. And you zoom in. Now this is a star. This is about 1,000 solar system size. And now you see what you're seeing here is a star that's forming, and there's a disk around the star. This is the reason you have a disk is because the finite angular momentum, when the material tries to fall onto the star has gravity. It grabs all the gas around it and try to let the gas and rocks to fall onto it. But because of the material has finite angular momentum, as they try to fall, they start rotate around the star, which is a tiny point. So you typically form a disk around it. And they also make a jet. You can see the colored outflow. This is the central star. You can see now this type of image, the shape, actually it's similar. You can see observationally that you have a central bright star that's just forming. You have dusty gaseous material that's accrete, fall onto the central star, and the star makes a bipolar jet coming out of it. So this is fairly common seen in a forming star system. And you zoom in space and also evolve in time. And gradually the star radiates strongly. The radiation is going to hit on the gas and star around it, dust around it, and try to, so you now imagine yourself flying through the dusty gaseous disk. Now, for alert students, you might have seen an object forming in that dusty gaseous thing you're flying through. That's presumably a planet, like a massive one, like Jupiter. And again, the Jupiter itself has gravity, and since it's so far away from the star, so the material around the Jupiter respond to Jupiter more than they respond to the star. So that material forms a disk around the Jupiter. So you can barely see it now, but gradually you see the rocks, the object area. Oops. And this is what we think during the formation stage of a planet. It's very hot. It looks like molten, but you have material around it. The sun shines over here, cause a shadow. All that are being observed. It's a real effect where we can see shadowing effect in disks causing by structures casting a shadow, which is quite amazing. And so the journey we just went through is what we envision, a star forming region that's fairly large, 10 to the 5 or 10 to the 6 times the solar system, but inside of which there are hundreds or thousands of stars are forming. And each star would be the flyby that we just did as you fly towards that central star. And around that, you get some planet formation out of the gas and dust. Okay. So this is just a montage of putting that together, a sequence of events where you have a cloud of gas and dust, and the central region will form. Some stars will get formed. It takes about 1 million years, and then the star would radiate and clear out a big hole. But the planets are too massive, so they stay, and ultimately they become what a quasi-mature planetary system. With both the central star that's just formed a few million years, and the planets are just, and then they evolve to billions of years, like our solar system. Okay. So I'm going to highlight these 2 stages. One is when you still have lots of gas and dust around the star. That is essential because if you think of a planet, Earth, right? It's most of the mass of the Earth is dust. If you realize it, dust and rocks. They're not gas. And Jupiter is mostly gas. So if you say, oh, ultimately I want to form a planetary system like solar system, some are in rocks, some in gas, you want to do that before the dust and gas are all gone. It turns out observationally, we observe many, many such disks, and we find that for older disks, the dust and gas are all dispersed. So in other words, you lose all the building material for planets. So that immediately tells us that if you want to form any planets around a particular star, you have to do it very, very quickly, within a few million years. Well, quick in the cosmos time scale, because in the end, this system lasts 5 billion years. Gig years, right? So it's 1/1000th of its lifetime that you have to quickly use up all the material you have to form all the planets. Otherwise, they're all being pushed out, being dispersed away. So to put in perspective, if you live out to say 100 years, corresponding to 5 gig years, and if you want. And if you ask what does 5 million years mean, it's about a month out of 100 years. So it's, I think in Chinese it's called 满月, right? So basically, during the first months of this whole planetary system, you've got to form all the planets quickly, and then otherwise you lose a chance to form planets, and then it's going to live out to 100 years. In human lifetime terms. So that presents huge amount of challenge because everything was still kind of violent, and they're accreting onto the central star, they're settling, and you're then telling all the gas and dust, oh, get organized quickly to form Earth, form Mars, form Jupiter, and Venus and Saturn and all that. And then the radiation is going to clear out the rest of the dust and the gas, and then we're left with a relatively clean system like a solar system. So that's pretty amazing. So Are there others, quote unquote, planetary systems in addition to solar system? The answer is resounding yes. So this is somewhat a busy plot, but let me try to orient you. The horizontal axis is what we call separation, namely the distance between the planet and their central star. So for example, Earth, E here, I'm assuming you can see my cursor. So it's at 1 AU, it's normalized by that distance, and its mass is normalized in terms of Jupiter mass is 1/300th. So all the purple circles here are solar system. This is Mercury, this is Mars, this is Venus, this is Saturn, this is Jupiter, right? The Jupiter is at 5 AU and it's at 1 Jupiter mass. So that's the 8 or 9 solar system planets here. And all the dots here are observed planets around other stars, not the sun. So we saw by eye, looks like 3 populations. There's a bunch of massive planets because their mass is around Jupiter or higher. So they go up to 10 Jupiter mass. So lots of other exoplanets are massive, very massive. They're 10 times, 5 times, 3 times Jupiter mass or around Jupiter mass. And they're kind of at the distance of Jupiter to their own parent star. So they're at 1 AU, that's closer to Jupiter. Some are really close, 0.1 AU. And that guy is really too close to their parent star. But anyhow, so that's seems to be one group, that's the blue one. And then there's another group, the red one, their masses is also Jupiter and it's massive, so lots of them are gas, and they're really close to the parent star. This is interesting because if you think of where do you want to form a planet, the conventional wisdom is to say you don't want to form them too close because too close to the star, the material is too hot. When the things are too hot, it's hard for them to stick. By sticking, I mean you want the dust particles to coagulate and grow. And if the radiation too intense, it gets they get deassociated, and then you can't really grow building blocks efficiently. So the conventional wisdom would put them way out here to form. That's far away from the central star and colder. But nonetheless, we see a big population of exoplanets that's very massive and they're very close and to their parent star. And then there is what we call super Earth population. So Earth is here. So that's 1 Earth mass. Over here will be 3 Earth mass. Above there will be 10 Earth mass. So there's huge number of them. That's Earth to 10 Earth size. Earth, 3 Earth, 10 Earth. And a count of Neptune. Neptune's here. And they're closer than Earth. And so that's another puzzle. How do you form planets that's 10 Earth size and closer? Now, astrophysically, we understand that there is what we call observational selection effect. In other words, if you put Earth around another star, they're so far away from the parent star and they're so small, the detection technique is not sensitive enough to detect it. So as you can see, all the detection is kind of to the left of this line here. Basically, all the planets that occupying in this region, in this part of primary space, they may be there. I mean, they are maybe Earth's mass, but they're just so far away. And it's just very, very hard to detect them. So the fact that we don't see much planets over here so far in the exosolar planets population doesn't mean they don't exist. It's just that the current technique are not sensitive enough to detect this part of the parameter space. Although what we do detect so far look to be very different from the solar system. Okay, so I'm going to say a few words on the detection technique. So here, one detection technique is what we call transient. So what you have is a planet moves in front of the star and moves away. Okay, just goes around and around and around and around for billions of years. Now, what's going to happen is that, which is quite amazing, is you observe the brightness of the star, which is the flux of this red line here. When the planet comes around in front of the star, you block out a little bit of the starlight. And then when it moves out of the away from the star, and then the star brightness restores back to the original brightness. So there's some error bars. This small blocking effect is observable by very sensitive telescope. And that amount of blockage tells you how big the star is, and this duration of the blockage tells you how fast this thing is moving, the planet is moving. Of course, Mercury goes around the sun, a few hours or days, and the Earth goes around the sun in a year. So based on the time duration of this blockage, you can tell how far the planet is from its parent star. So you get the size, you get the quasi-distance in period. So that's one technique. And this technique typically is very sensitive to those red ones. So that's called transients. And as you can see, if they are far, far away from their parent star, it takes years for them to come by again. And we just can't wait that long. So that's what I meant by selection effect. There may be those planets just because it's taking 100 years for them to come by, or 50 years for them to come by. No graduate students can do their thesis for 50 years, right? So they do a 5-year thing. So 5-year thing is maybe over here, the periods. So, and they're predominantly sensitive to nearby, the planets who are close to their parent star. That's why the distance is so small. Another technique, if you remember your celestial mechanics, there is a star, there's a planet, there's a center mass of that two-body motion. The center and one mass is star mass is much bigger than the planet mass, but nonetheless, the center mass is not co-locating with the center of the star. So in reality, the planet goes around on orbit, the star also goes around on orbit. But observationally, the star orbit is so tiny, you don't call it orbit. All you see is star is wobbling. It's not the way you see the star wobbling is not to actually see the star actually wobbling. You do it by detecting through Doppler shift of a spectral line that's emitting from the surface of the star. And as the star moves away, the line shifts, red shifts, as the star moves towards the observer, and you get blue shifts. So by building very sensitive spectroscopy detection, you see the periodic line shifts, what we call radial velocity. And that radial velocity, that wobble of the star is purely caused by the planet, how massive the planet and how far away is the planet. So through that kind of modeling, you can get the planet mass. So for those, they are, the blue ones are from that. So you can see predominantly the massive planets are detected through that technique. So I should move on. Are there any questions so far? No? Okay, I'm going to keep going.
I have a question. So this would have to be, so for example, this Doppler thing, if there are two planets, have people kind of figured out how to take that into account?
Excellent question. So what I'm showing here, this was actually a discovery paper, and I think those two guys got Nobel Prize back in 2019, or or 2018, I forgot. When you have two planets, what you get is not a perfect sinusoidal signal, because you have two periods in it. And then you do, and if you were able to monitor for many cycles, and then you do Fourier transform, and you fit those, and you realize, oh, there's actually multiple planets. In fact, some of the discovery papers does have multiple planet system.
Thanks.
Yeah. Okay. Excellent question. So now, like I was mentioning, you have to form planets very, very quickly, so that once they're formed and their environment is relatively clean, they will sit there for billions of years, not sit there, they go around their parent star for billions of years. So in terms of a human lifetime, the first months is really exciting and violent. And then after the first month, things become mundane. They just go round and round and round and round for 100 years in human lifetime terms. So that's whether you call it boring or fantastic, that's your personal taste. But during the first months in human, or in a couple million years in the lifetime of the planetary system, you have dust, you have rocks, you have gas, and you really have to do things quickly. So this is what Perseverance sent back, right? So this is what Mars really look like. I mean, they're rocks, they're dust, they're rocks, right? There's not much air, atmosphere. Otherwise, we probably be very excited about going there. And it's apparently very little water also. So, and how do we do that, right? So here's kind of the schematic thinking, right? And now you're looking at this dusty gaseous disk sideways. The light bluish is the gas component. They form a disk around the central star. And then all the red dots are what we call dust particles. So, I mean, this is literally like, I know Singapore is extremely clean, but if you come to Mexico, when the dust storm comes, when the wind blows, the air can be mixed with dusty particles. So, and the star is really young and energetic. It's irradiating, sending out radiation, UV radiation, X-ray, optical, and so on. All that photons is going to hit the disk and hit the gas, and it's going to evaporate the gas and heats it. And the dust particles at the same time gets mixed around by the turbulence in the disk, and then they settle, and then they coagulate. They find other dust particles to grow in size, and then once they become heavier, they settle to the middle of the disk, because that's the gravity that's all pull them towards the middle of the disk, and gravity pulls them towards the central star. And then the photoevaporation clears out the gas first, and you're left with debris disk and bodies and planets, basically. So that's kind of, there is strong observational support for all four stages. So within that 1 month, quote unquote, of the planet formation stage, you can still finding candidates that look more like A, look more like B, or C and D. Okay, so that's kind of what we think is happening. Let me skip that. Now, how about the dust? It turns out it's exceedingly complicated. If you ask yourself, where does dust come from? Remember the movie I showed, a lot of them are dust. So the dust of this red dots here all come from interstellar medium. And if you ask what are the sizes of the dust in the interstellar medium, they're micron, tiny. And people measure those sizes from the spectroscopy. But I mean, obviously, we see rocks on Mars. We see rocks on Earth. Don't have to go to Mars to see rocks. And Earth is a big, giant rock, right? A 6,000 kilometer radius. So apparently, the dust has to grow to 10 micron, 100 micron, a millimeter. Now, when you're a millimeter, we can measure them again, centimeter. And then the kids pick those pebbles up and throw into water, the skid rocks and pebbles. That's about, several centimeter. When you are dealing with a 10 centimeter rock, that's a huge rock now. And we see all that in astronomy, in disks, through different ways of detecting their presence. Although their structure may not be as compact as what we see here, but we can infer their size. But then we lose detection because we don't know how to detect, a 100-meter object, because I'll come to that. Then ultimately we get Earth, we get different satellites, and we get Jupiter. So the way to detect dust particles from micron to centimeter is actually through what we call thermal reprocessing. So I went to the web and found this. I hope you all recognize what I'm showing now. On the left is the satellite image of where you live. And this is an infrared satellite image. So in infrared, what happens is either sunlight or the heat from the city itself heats and generates infrared emission. That's from heating. Same goes on in the disk around the star. You can get optical observation of the star itself, like we see the sun, but their light, in optical light, the UV heats the gas and dust, and the gas and dust reprocess that emission and emit in radial, in sub-millimeter infrared, and that's thermal emission. And that emission is very sensitive to the amount of dust that you have. Here, you'll be sensitive to the amount of aerosol in the air. And so that is, in astronomy, we detect the thermal emission of the reprocess being heated by the central star. So that's called sub-millimeter. So the best sub-millimeter telescope is actually an array up in Chile called ALMA. That's my map of Chile, southern and Brazil, and in the high plateau deserts. And they build arrays of dishes, and that's sensitive for millimeter and sub-millimeter. And this is by far the largest, sub-millimeter array. So let me just show you what it means for us, right? So this was back in 2008 of an object, MWC 758. Don't ask me why it's called that. I don't know either. But it's very bright and isolated. And we know there's a star. And we know there is thermal emission around it. And then we look at this, we say, we detect the dusty gaseous disk around the star, because that emission apparently is not from the star. Can you see the difference here? So, but that's the resolution unit. But already we say, finally we see dusty gaseous disk around the star. We can use the intensity to estimate how much mass is in that object, in those disks. That's the depository of material where you're going to form planets, precious material. That's 2808. 2015, the early stages ALMA. It turns out, yes, that's indeed a star, but there's a hole around it. And that bright emission you saw earlier was actually separated out into two bright regions. And then that's where a lot of dust are, because they're so bright in reprocessed thermal emission. That means a lot of dust in those regions. And that's 2017. It turns out not only there's a hole, there's actually a ring around it, and there's a dust concentration, not dust concentration. That's important for us. Now the angular resolution is this small, because in order to say anything about planet formation, if you look at images like this, you say, where does the planet form? You can just put it up just about anywhere. Here you say, well, probably not there. And that's the likely candidate because you have a lot of dust already concentrated there. Why don't you make planets there? You have so much supply. And that's even smaller, right? So that's a collection of up until maybe 2-3 years ago. And ALMA did a big, huge survey, lots of observing time. It turns out the rings, the spirals, the bright features, the gaps, are fairly common. Unlike low resolution ones, you just see big blobs and smudge around it. So that's extremely exciting for us who want to understand planet formation. So are those rings and concentrations like that imply planets are being formed there? That's the question. So let me say a few words of gas and dust interaction. I'm trying to make it as basic as possible. So you have this gaseous disk around the star that's the dust is being battered around, and there's a turbulence. It turns out, as you can intuitively understand, when the dust particle is tiny, like micron, they are really enslaved by the gas. So that we call fully coupled limit. You go to the other end, if you have a rock that's a meter size, the air molecules are not going to do much to it. That means it's going to collectively acting as a drag, but you're not going to move turbulence around a meter size rock. So that's mostly almost decoupled. The ALMA observation is most sensitive in this band from millimeter up to centimeter. That's what we call, in physics terms, two fluids. In other words, they're not fully coupled. And then one fluid is enough. You just add the density together. They're not decoupled. And you kind of treat it as a two fluids. There is a viscous drag between the two fluids. That's the most interesting stage in terms of planet formation because I'm not going into details here. It turns out there are size barriers that they have to jump through in order to become a rock. Once you become a big rock and through gravitational attraction, you can keep going from there. So this is actually one of the reasons motivated building the ALMA telescope is to understand the physics in this region so that interstellar supply of micron can go over the millimeter centimeter barrier all the way to meter-sized rock. So I think I'm quickly running out of time. I'm going to skip all this. And the way to do that is, at least for us, is large-scale 2D and 3D numerical simulations. This is also what Los Alamos National Lab is well known for, is a huge amount of computing resources. And so I'm going to quickly show a few examples of how we do computing. One of them, the idea is let's form vortices in this disk. Just think of Earth's atmosphere. Maybe it's typhoon for us, it's hurricane. Maybe you can form big vortices, and in the vortices you can trap dust. Once dust gets trapped in there, and maybe they will compact and promote the formation of planets. That's the general idea. And one of the key work we've done over the years is to understand what processes that can lead to vortice formation. And this is some of the work I did back more than 20 years ago. And I learned a lot from atmospheric science people. They worked really hard to understand the formation of tornadoes, hurricane, and typhoon, and in a rotating Earth's atmosphere. What I learned from that is how to do it in a rotating disk. How do you form vortices? And in there, indeed, we were able to do that. And this is a simulation of a disk around the central star. If you were to put in the forming planet, the planet will perturb the disk in such a way you'll form lots of vortices, and those vortices in gas are going to trap dust inside to promote further formation of planets. Let me skip this. And this is another run indeed. we are now doing both gas and dust together. And this is gas. You need to see the big vortex formation in gas. And then the dust also in response to the gas vortex, and they get trapped. So this is 10 micron size, a millimeter size, and 1 centimeter size. Oops. I apologize. So this gas drags the dust around, and we tried for 3 different dust sizes and how they each respond to those vortices, and they can form those horseshoe-looking structures with vortice structures very similar to what observations have shown. Let me keep going, and then when we do very localized, not only global simulation, but coupled with that, we use very globally coupled and also locally highly resolved vortices. We actually see further instability spirals. All those lead to different features of dust and gas that's being tested by observations right now. So in real life, this is actually also, there's strong evidence of that. What's shown here is a real satellite image of a hurricane that's being formed and is heading through Caribbean towards America. And this is Sahara Desert, Africa. And the red color is the aerosol density. So when the wind, so there's a huge amount of aerosol density, and this is supposed to be a movie, but I didn't find it. And this aerosol gets dragged into the hurricane here, which is mostly air. But because the dust, air, gas interaction is significantly weakened, this hurricane later on as it passes through, it gets dissipated away. So dust actually became useful in this case. And that's what we similarly were studying in the protoplanetary disk, is how the dust and the air would interact and would either help promoting the vortices or destroy the vortices, so limit the planet formation. So I think my time is up, so let me quickly, and this is a simulation we've done that ultimately showed how the physics process we're studying can produce mock-up images that look very similar to observation. So I'll conclude using this slide. This is what I was showing earlier for exoplanet population. The solar system is over here. This is Earth, this is Jupiter, and there's a different population using different techniques. Now, using the modeling of those dust features that I showed, and that's 1 month old of those systems, we inferred there could be planets in there that's forming, and that's how they're making those features we see: the rings, the vortices, the dusty gaps, and the horseshoes. And then by modeling those features, we can infer the mass of the forming planets, and that's how we get those places, those symbols there. They're far away. Again, because if those things in this case are too close, then the ALMA telescope can't resolve them. So they're far away, and they can be observed right now by those features. And their mass is actually neither Jupiter nor Super Earth. It's right in this gap. So in a way, the mystery deepens, because we're now finding ones that's as small as 10 Earths, although it's going to be difficult to detect their impact. We're not finding Jupiters, and then we should be finding them, because they would make a huge impact in their disk environment for us to see. But at least for the ones we've studied, none of them seem to be coming up to that. Although they still get time to grow, so maybe they will eventually migrate inward and grow in size, at least can explain this population. But they're not going to become smaller to account for that population. But there could be a hidden big population we're not observing right now, but ultimately will become super Earth. So with that, I think there's huge amount of subject that's not understood, and a huge amount of work to be done and exploration to be carried out. With that, I thank you for your attention. I should stop here. Thank you.
Thank you, Li Hui, for the amazing talk. Any questions from the audience? You can choose to unmute yourself and ask, or you can type your questions in the chat box. Okay, I'll start with the first question. So Li Hui, the slide that's just before this summary slide, you mentioned about that your simulation can sort of explain why Saturn has a ring, is it?
Oh, sorry, no. What this meant to show, I apologize. I'm zip by too fast. Because the red colors are observation. Well, in this case, red colors are actually mock-up observations, but they look very similar to observation. And we use our models to say if there is a forming planet that with the mass sub-Saturn, say 0.5 Saturn mass, they're going to generate features look like those rings. So we're using the similarity between the modeled system and the observed system to say, we think there is a sub-Saturn mass planet that's forming. That's why, and that planet is interacting with the gas and dust around it. That's why you're making those features. So that's how we were able to say, oh, there is a sub-Saturn mass at that location.
So do astrophysicists know why Saturn has a ring? I mean, what are the conditions that facilitate the formation of a ring around a planet?
So the details of the ring dynamics is still a very active subject, but to have a ring is actually not very surprising, because as I was saying, every planet is formed from the dust and gas. So there is something left over around it. And the ring is actually mostly dust. So very little gas. So the dust particles, one key feature of the pure dust particles, they don't have pressure. In the gas, like right now when I speak, the sound waves propagate through air, and my wife will hear that. And if I'm surrounded by pure dust, then they don't carry pressure. So it's very difficult to generate any signals through them. So the dust rings actually is not surprising in terms of being left over during the formation process. Now, to explain why this many rings, why there are gaps, why there's this, why there are, that's a far more complicated issue.
And why is the ring so flat?
It turns out if you kick it, it would oscillate vertically and will damp, and then it will become it's a minimal in potential in their action integral. Okay. So it's actually, they prefer to stay in the middle.
I see.
And there's no pressure to puff them up.
Okay, thank you. Chelsea, you raise your hand.
Hi, yeah. I have a question about something you just very briefly mentioned way back in the introductory material. You mentioned that astronomers have actually observed shadows cast by planets, and I was kind of surprised that that's been done. So I was kind of curious, what like wavelengths has that been observed in? You know, what angular resolution? And you know, I know it's not your exact research area, but like, what does the shadows tell us about the planets? Presumably their size, but anything else?
Okay, so I spoke, so I didn't include the image like that. So what's happening? First of all, it's observed mostly the shadow effects mostly in micron, so not sub-millimeter yet. So what happens is there. Let's say here, just imagine this is a highly dust concentrated region. which is true. This is a sub-millimeter, so it's highly concentrated. So if you look sideways, this looks like a mountain. So the starlight coming out from here, hitting this thing, and then you in the micron images, not sub-millimeter, you actually see a darker region behind that feature. So that's the shadowing I was talking about. So compared to the fake movie that's made by NASA, there you see a shadowing effect from the planet. But in observation, we're mostly seeing the disk features. The disk is not completely monotonic. There are local maxima and minima. So that those scale height change variations produce the shadows. Does that make sense?
Yeah, that's great. Thank you.
Okay, thank you. Yidong.
Yeah, hi. So when you talk about the this rings being swept out in the disk, so the gas and dust that's left over in the disk, what's the ultimate fate of it? Will it eventually accrete onto the planets, or does it get blown out into interstellar space?
Excellent question. So let me use this figure. Actually, let me use this. This is real, right? So this hole is already telling us for the source. They see this is 50 AU. You know, the Earth is at 1 AU from its star. This is 50 AU, so this hole, the radius is 50. So this system is already evolving at a stage where the star is clearing out a hole of 50 AU size radius. But there's still dust at far away distances. So that's why the bright regions are dust emission. So if you look at this region, you say, how much dust are in that little feature there? It's probably 100 Earth mass in that big clump there. So you still got a chance to form planets. and usually the gas is 100 times larger than the dust. So if you have this much dust concentrated there, you multiply by 100, and presumably all these regions are a lot of gas as well. So this system is at a stage where it's about a couple million years old. There's already on its way losing mass, but you still got a chance to form planets. If you wait 10 million years, all of this will be gone. But you're left with hopefully bodies and planets, rocks, that's already, that condenses out of coagulates out of the dust particles. And for the massive planets, they will grab the gas around it. So there's interesting dichotomy that for Earth, the mass is not big enough that it cannot retain high enough gas because the surface layer will be heated by the sun. It has a temperature. And so there's a scale height, and then the gravity of the Earth is not strong enough to retain a huge amount of atmosphere. Jupiter, on the other hand, when they grow to be massive enough, the gravity of the proto-Jupiter is big enough. It retains they keep retaining gas around it, and grow the gas around it, and so that's why it becomes gas giant. So so for this particular system, if you wait. If you go to its earlier, like a fraction of a million years, probably there's no hole or a very tiny hole. And then by this time, they have a big hole. By another 5 million years, probably all those features are gone.
So there's a related question, which is that, people have been speculating that there could be planets far beyond the orbit of Pluto, right? So could this kind of line of research eventually help us to kind of figure out the probability of that?
The short answer is we don't know. And this is a great question because because solar system says, all the planets are formed kind of within this hole, basically. And if they don't migrate much, one Earth. And if you ask yourself, are there enough building block material inside our 50 AU hole? The answer is yes. There is enough material, barely enough, not plenty, but it's kind of enough to make those planets. But then currently, at least maybe due to the observational limit, for those small disk regions, we can't observe them with high resolution. So we really don't know what's going on there. But on the other hand, at hundreds of 100 AU length scale, we see lots of action. And the conditions are ripe for planet formation. So, and then you go even further out, then there is a question is, if the planet formation is so common that's going on all the time, you could have another kid wandering from your neighbor into your own house, and they may appear very far, but they were not born from this house, from this star. So we've seen those free floating planets as well. So every time when you get an object, you have to be careful as to whether they're truly orbiting around this star, or they're just waving bye-bye, but since they're so far away, it takes a long time to trace out their motion for us to be confident whether they actually belong to this quote unquote solar system or they're just a free floating planet. So, and one of the biggest lessons we've learned from all this, the past 10, 20 years, is that the planet formation, A, is very robust, B, it has a huge variety. So, which makes things both interesting and hard. I hope that addresses your.
Yeah, thanks.
Any other questions from the students?
There is a question in the chat.
Oh, okay, thank you. Okay, so a question for you, Li Hui. Is our sun and solar system too old, or are there other systems older in terms of the evolution of gas and dust?
So the lifetime of sun, the sun is kind of at its mature age, 4 billion years. When you go to 10 billion years, the sun is what we call, it's going to expand. We see that in other stars like this with mass similar to sun. So the way astronomy understands stellar evolution is not to stare at one star and follow 10 billion years. It's just no one lived that long. Instead, we look at billions of them. So some are really young, some are really old, and we say, they're same mass. So we say, okay, for sun, when the sun was only 1 million years old, it probably looks like this. When the sun is 10 billion years old, it's going to look like that. So, so there are systems, there are definitely lots of systems older than sun, lots of systems younger than sun. And they all have planets. It's just that when it's very old compared, when it's like the sun that's older, you just get systems like, I had an image. You just get systems like, I'm having trouble finding it. Oh, here. You get a system like this, current solar system. There is no gas and dust. But when it's really young, you get gas and dust. What I was trying to say here is the duration of dust and gas live is about 5 million years. That's really short, 1/1000th of its lifetime. That's what I mean by 1 month compared to 100 years in terms of human lifetime. So you got to form all your planets within the 1/1000th of its lifetime. Otherwise, all the building material are gone.
Thanks. Another question from the chat group. Are there many Earth-like exoplanets that can potentially support life? And I have a follow-up question to this question, and that is, how do you experimentally or observationally determine whether some exoplanet super far away has life?
Okay, so you can see this is a plot made back in May of 2019. So that's 2 years ago. And now the number of dots here, which are exoplanets, has gone up to 4,000 or more. This is maybe 3,000 something, I forgot. So just to orient you, the horizontal axis is the distance to their parent star. So each dot is a planet, like Earth is here. Earth is 1 AU away from the sun, okay? And the mass is 1/300th of Jupiter. This is normalized by Jupiter. So this is Earth. So if you ask, are there other Earth-sized planets out there around other stars? Answer is absolutely yes, because you see there are many planets that Earth mass, but are they at the right distance from their parent star? At least in these detections, they're kind of too close to the parent star. Now, for the so-called habitable zone, so if you put if you put a planet too close to their parent star, it's too hot, and it also goes around the parent star very, very fast. And if you put it too far away from the parent star, they're too cold, and then they also go around very, very slowly. So and all of that has implication for water formation. When it's too hot, water gets evaporated. When too cold, it's always in ice form, and so on and so on. So, and for liquid water and the right pleasant temperature range, that's believed that's more suitable for life as we know. Then there is a habitable zone, which is kind of over here. So there are planets now being discovered that would reside in what we call habitable zone. So as more satellites are being built and will be more sensitive to this region, and then we will accumulate more data as to whether those planets, at least in the bulk property sense, in terms of distance to their parent star, their size, their mass, their periods, and all that, their temperature, and how much atmosphere are there, and that becomes the key parameter we use to decipher whether they can harbor life. And we mostly use liquid water formation and temperature as the main criteria. Now, as responding to Albert, I'm not a big expert in that. My reading on that subject is to see the lines. the atmosphere, sometimes there are winds come out of it because just from the stellar irradiation, it drives winds. And then from the wind, you can get elements exposed, and then they have emission. And then you can infer other material. I mean, that's life supporting, especially organic molecules. That's believed to be necessary for life as we know, as the building blocks. So those are some of the key ways of inferring possible life on habitable planets, planets in habitable zones.
Thank you. Yidong? Yidong, you have a question?
Sorry, I forgot to load the hand. Yeah.
Okay, another question that's related to habitable zone by someone in the chat group. Does the habitable zone depend on the mass of the star?
We don't but I think the short answer is we don't have enough data yet to be confident about that. But if you just calculate, if you have a formula and say you want the temperature and the period and the density of the planet to be in some region, and then those parameters do depend on the stellar mass because the temperature is the heat. Most of the planet heat is coming from the sun, from their sun, as you probably know, being living in Singapore. So that temperature, if typically the more massive the central star is, the hotter it gets, more radiation. So that determines the habitable zone distance away from it. So it does have a dependence on the central star mass. But things can get complicated very, very quickly, depending on other chemistry issues. So the short answer is yes, it has dependence on the stellar mass, but it may not be as simple as linear, for example.
Okay, I will ask the last question before this seminar ends. And there are quite a lot of undergrads in this audience, and they will probably be wondering, the stuff that I'm studying now in undergraduate physics, is it of any relevance to if I want to do astrophysics next time? For example, statistical mechanics. Is it of any use? Quantum mechanics or whatever. So maybe you can give some advice or some comments to the undergraduates here.
So the answer is a resounding yes. So I did my undergrad in physics in Peking University on solid state physics. I was building what do you call that? I even forgot the name. Locking amplifier and laser systems. One laser pass goes through a semiconductor material, has room temperature. Another one I put in the liquid nitrogen, sorry. And I studied energy bands, how it varies as a function of temperature. I spent nights and nights, building the laser system and the locking amplifier to get the signal to measure the energy levels and all that. And I think I did a great thesis. Then I went to my grad school and I got exposed to astronomy. I said, wow, that looks even more interesting. But the physics trained me. I mean, solid state physics, statistics, the celestial mechanics trained my thinking, my technical skills, math skills. And then the thing about astronomy is you can never do hands-on experiments on those. And you can't send graduate students to take samples, go there. But that's where your imagination can either go wild, or you really imagine, that's such a big, huge sandbox for us to play in. I mean, it's the universe that you learn, you make progress on. So it's fascinating. So I would say all the math, physics intuition, physics understanding training you get in your undergrad physics lays a very solid foundation for exploration. So I think doing physics in undergrad and doing astrophysics in grad school and as a career is a great choice.
In your present research, are there a lot of statistical mechanics?
Oh yeah, well, so some of the things I skipped. Let me just use this. It depends. So for me, I used some, and a lot of astrophysics uses that as well. Like when they have to do nuclear synthesis calculations, that's a lot of statistical mechanics and entropy calculation stuff. And in plasma astrophysics, it's also entropy. In this, what I was trying to convey here is we're solving big rate equations It's one type of Monte Carlo statistical mechanics, if you want to call it that way, but it may not be the particular ones you're familiar with. And the issue is in any, if you were able to send a graduate student in a solar system when they're still young, and then measures a chunk of matter, it's like, you know, rover goes in to grab a chunk of air during the formation stage of some planet. And you open it up, you measure the size of the dust, you'll find out, oh, there's some are micron, some are 100 micron, some are millimeter, some are centimeter, some are 10 centimeter. It forms a broad distribution. So the question becomes, why do they form particular distribution? And what are the processes that allow dust particles to grow bigger, and what are processes to break them apart to become smaller? That's called fragmentation. So it's a dynamic rate calculation balancing of size growth and size fragmentation. And we do that on the fly while evolving hydrodynamics. So it's a subgrid physics going on. So I would say that's a bit of statistical mechanics that we have to employ there, together with fluid dynamics in order to understand planet formation.
Thank you very much. So we really want to thank Li Hui for spending so much time giving us an introduction, making sure that we understand the basics of what he's talking about, and it's just very fascinating. So let's thank our speaker, Dr. Li Hui, for this talk.
Thank you.
Thank you very much. Thank you very much.
It looks like I keep my track record. I'll always go over time.
No, it's good. It's good. I'm sure the students have a lot of questions. So the link of this talk will be put up soon as Li Hui sends us his PowerPoint file. And you know, if you have any questions for him, just email him. You know, and let's hope that this will be just the first of a series of talks on these interesting topics. Thank you, everyone, for attending this seminar. Bye-bye.
Thank you. Bye-bye.
Bye-bye.